Hello, it's a great pleasure to present to you at the conference today. My name's Adrian Hopgood. I'm Professor of Intelligent Systems at the University of Portsmouth. I've entitled my talk today AI literacy. That is to say, ensuring that everybody in the population has a good basic understanding of artificial intelligence. So I'm going to start by covering what is AI literacy under three headings: AI techniques and uses, how AI works, and life with AI. I'm going to cover the first two of those topics, understanding AI and its uses, together in a historical context. That is to say, I will argue that to understand current AI, it is best to look at how it's an improvement on the versions of AI that came before. And then I'm briefly at the end going to talk about life with AI, covering things like ethics, law, impact on society, and the environment. All my slides from today's presentation are available at my website, adrianhopgood.com/presentations. So starting with what do we mean by AI literacy? I'm citing two sources here. Castle, Otero et al. Break it down into three key components, and this is the way I've structured my talk. Learning about AI techniques and its uses, learning about how AI works, so that's the underlying techniques and technologies, and then learning for life with AI, what its impact is on life and society. Klein, just a matter of a few months ago, has proposed a structure for delivering an educational program in AI literacy. And Klein argues that you need a basic understanding of AI, of how AI works. But Klein goes on to say that an AI literacy educational program needs hands-on opportunities to understand how the technology works, so real practical experience. They also then talk about discussing and analyzing ethical questions about AI technologies, how to interact effectively with AI. And then finally, they really emphasize the point that AI skills are not just for computer science experts. And I think this is the key shift when we start to talk about AI literacy, because until fairly recently, AI education and training was very much restricted to computer scientists, whereas now the argument is that everybody needs a basic grasp of AI. So, talking about what that idea of a basic grasp of AI, let's turn to what it actually means. What's the definition of AI? Well, conventionally, it would be something like this: mimicking human mental faculties with a machine, or mental capabilities with a machine. And this kind of broad definition of AI has been around for a long time. And it's quite ambitious, and it doesn't really specify the technologies. It raises a few questions. One of the questions it raises does the AI actually need to work like the human, or are you just interested in its outputs? Similarly, is the aim to match or indeed exceed a human? Because certainly we see currently some forms of AI exceed human capabilities in certain respects, so particularly things like speed and consistency. So a slightly tweaked version of that definition might be that AI is performing tasks with a computer that would otherwise need a human. So this similar definition, but it's I've now removed the word mimicking, so that gives you a slightly more pragmatic, practical view of AI. But it still raises some questions. Does it need to be able to explain itself? And this is quite a hot topic at the moment, the whole idea of AI explainability and related to that, issues of trust. Is it just about humans, or is animal intelligence relevant? Or for that matter, is all biologically inspired computing a form of AI? And there are no right answers to these questions, but there are multiple perspectives on AI and how it might be developed. Another consideration is that what we understand by AI is constantly shifting. And here's a quote from one of the AI pioneers, Rodney Brooks, who says that every time we figure out a piece of it, that's a piece of AI, it stops being magical and we say, oh, that's just a computation. And to give you some examples, when I first started working in the AI field, chess was considered a major challenge, which is now effectively solved since the mid 1990s, when IBM's program Deep Blue beat the human chess grandmaster. Character recognition was a significant problem, recognizing handwritten characters in particular. And I'm going to give an example of that shortly. But that's now effectively solved and in day-to-day use, and we tend not to think of it as AI. We tend to think of AI as the next big challenge rather than things that have already been achieved. And speech recognition falls into the same category. So although AI is very much in the spotlight at the moment, it has been around for a while. You can argue about when it started, but I would like to point to Alan Turing's paper of 1950. So that's 73 years ago, when he proposed in his paper, the opening sentence is, I propose to consider the question, can machines think? So he's, in his opening sentence, he's opened up the possibility of machines thinking and displaying intelligence. And in that paper, he goes on to propose what he calls the imitation game, what we often now call the Turing test, where he argues that if you cannot tell whether you're having a conversation with a human or a computer, then the computer system has passed his Turing test for intelligence. Now, Turing didn't actually use the word or the phrase artificial intelligence. The first published use of that phrase was 5 years later, in 1955, when McCarthy et al. Published a proposal for the Dartmouth Summer Research Project on Artificial Intelligence. We now tend to refer to that as the Dartmouth Conference. It happened a year later in 1956, but the publicity for it was published in 1955. And it was a gathering of scientists who were starting to work in this field, and you can see some of them in this photograph. Now, AI, I would argue, can be broadly broken down into two families of tools. There is a long tradition of knowledge-based intelligence, which I've put in the red circle here, sometimes called symbolic AI, and it's textual and transparent and logical. In the blue circle, we've got what I've called computational intelligence, and that tends to be where the focus is largely at the moment, and that's data-driven. Two completely different approaches. So the knowledge-based form of AI tries to capture human expertise in a computer system and apply logical application of that knowledge to new scenarios to interpret it or give a judgment or a decision using techniques like rules, cases, models, etc. Computational intelligence, on the other hand, is data-driven and specifically looking for patterns in data. So the main tool is machine learning, and the main technique for machine learning is neural networks. We are sometimes also referred to deep learning, which is essentially just very large neural networks learning with large data sets. There are some other techniques too, like operational research, which is a more mathematical approach. And then genetic algorithms are one of many techniques for finding optimal combinations of parameters, again, that falls into this broad category of computational intelligence. Then we've got some techniques that fall in between the two. Fuzzy logic, Bayesian updating have aspects of both knowledge-based and computational intelligence. Now, the earliest developments tended to be knowledge-based, but they're still relevant today. So let's look at some of those historic examples. So Dendrel, 1969, a very successful expert system. So that's a form of AI which acts as a sort of expert advisor. So Dendrel was for interpreting mass spectrograms, so a very specialist scientific field. Mycin was a medical application for diagnosing blood disorders. in 1976, followed shortly after by Prospector, a system for mineral prospecting. A very famous example, system called R1, and then through its iterations known as XCON and then XCell. That became famous because by 1986 it was estimated to be saving the parent company, Digital Equipment Corporation, $25 million a year by reducing the need to give customers free components when technicians made errors, because the system was much better configured using this system. But it's still current, so more recent examples, SmartGov for helping to design local government web services, Size Expert for interpreting seismic data, and pressure ulcer management system more recently in the medical domain. I myself started working in the field in the mid-80s. I was working for a company called Systems Designers International. I joined them in 1984, and by 1985 I was working in the AI field within that company, and I didn't respond to this particular advert because I was still because I was actually already working for the company. But I found this online. It's a New Scientist advert from 7th of February 1985 that clearly emphasizes that back in the 80s this was a booming field of AI. So it's not just in the headlines today; it has been in the headlines before. I'll briefly explain how knowledge-based programming knowledge-based systems work before moving on to the data-driven approaches. So knowledge-based systems are sometimes referred to as declarative programming. That is to say that the user declares everything they know and puts it into the knowledge base, and they don't have to be expert programmers to do that. They don't have to worry about what order they put the knowledge into the knowledge base. It's just a receptacle where they can enter their knowledge in a predefined format. And then this program called the inference engine applies that knowledge to new situations which arise through an interface by maybe some human interaction, or to hardware, or to data, or indeed to other software systems. And as I say, that sort of approach is still current, hasn't gone away. And I work with a company called LPA Limited, who've devised a graphical interface so that called VisiRule, which enables the users to design on screen various forms of knowledge in terms of rules, relationships, hierarchies, etc., and to declare them visually, and VisiRule will automatically generate the underlying code, which is sort of a language called Flex for representing all that expertise. And just an example that's in my textbook is to do with controlling or managing an industrial boiler that looks something like this. And you can devise rules for managing that boiler system. Production rules are the simplest form of rules, which are simply of the form if some condition, then some conclusion. In this case, if the pressure is above 1 megapascal and the release valve is closed, then you deduce that the release valve is stuck. More sophistication can be added by implementing uncertainty. So if the pressure is above that value and the release valve is closed, then the release valve is stuck with a certain probability. And those forms of rules can be implemented in Flex, as I mentioned, and on my website I've got some practical examples using the Flex language. Bayesian updating is a well-established technique for implementing uncertainty in rules. And in this approach of Bayesian updating, every proposition, such as temperature is high, water level is low, pressure is high, has a a probability associated with it, and those probabilities get updated according to the new incoming data and the application of the rules in the knowledge base. So here's an example of a rule which has these weightings on it, which are used to update the probability of the conclusion, the pressure becoming high. And here's a simple example that I found online at the CLIPS website. CLIPS is an expert system example programming language. And this is to help you choose a wine to go with your meal, according to whether you prefer dry, medium, or sweet wines, whether you prefer red or white wines, whether you like them light or full-bodied, the kind of meal you're having, whether it's got sauce, whether it's spicy, etc. And given this selection of responses, it's recommending a Chardonnay with a certain percentage certainty. So that's given you a flavour of some of the forms of knowledge that go into knowledge-based systems, or as I say, sometimes called symbolic AI. But it's not just about rules. It's not just about uncertainty. There's things like explicit models and stored cases, etc. And another form is fuzzy logic, which, as I mentioned earlier, is sort of on the boundary between symbolic AI and computational intelligence. And this uses rules expressed in using vague language, but there is an underlying precision. And the key point about fuzzy logic is that it doesn't have these kind of step responses that you get with the conventional rules or conventional applications of logic, but it's the conclusion scales with the degree of satisfaction of the conditions. And to give you a simple example, in the case of a digital camera, you want to adjust the aperture according to the level of light entering the camera, and that can be achieved with two simple fuzzy rules. If the light level is high, then the aperture should be small. If the light level is low, then the aperture should be large to allow in more light. Notice the vague terms in there: high, small, low, large. But the key point is that by using just this pair of rules, a fuzzy system could control the aperture of a digital camera. As the light level gets higher, the aperture gets smaller in a smooth fashion. And that's the key point about fuzzy logic. So there are various tools in the knowledge-based family of AI techniques, including rules, as I say, but also fuzzy logic, Bayesian updating, which, as I said earlier, have aspects of computational intelligence, things like case-based reasoning, modeling, etc. If we draw up a spectrum of intelligent behaviors, what's interesting is that these early successes in AI, very much driven by knowledge-based systems, tended to be at the top end of the intelligence spectrum, dealing with specialist human expertise and planning and so forth in areas like science, medicine, law. Similarly, at the same time, since the 70s, we've had very effective systems for automation. In this illustration here, we've got an automated car manufacturing plant, robotic assembly, and that's required things like coordination, regulation, reaction. So from the early days, we've had much success at both ends of the intelligence spectrum, but what's proved more challenging has been the areas in the middle, which is perhaps kind of surprising, because things like language, common sense, vision, perception are the sort of things that humans do with barely a conscious thought, and yet they are actually the more challenging aspects for AI, which have only actually in recent times started to bridge that middle section of this intelligence spectrum. And to give you a sort of flavour of why that might be, let's look at this photograph, which I've taken some years ago in my garden. And what you will see there is that there are three rabbits pictured. There is a pet rabbit in the cage here, a wild rabbit that came to visit, and a rabbit statue here. A couple of flowers as well. A fully sighted human can see that and pretty rapidly understand what's in that image and recognize the rabbits, even though only two of them are real rabbits. One of them is a statue. They're in different orientations. The pet rabbit is partially obscured, but nevertheless, you can interpret that image. That has actually been a major challenge, and it's actually only relatively recently that we've had reliable systems that could actually interpret those components of that image. But even then, recognizing the components of an image is not necessarily enough. There's the context. So here's an image of a tank on a street in London. So you could envisage an image recognition system that would identify that item as a tank, but there is some context here. It wouldn't necessarily want to interpret that as a threat or some sign of a military invasion, because that clearly is not the case here. This is not a military scenario. It's in the centre of London. There's traffic behind it. There are people on that tank who are not military personnel. They look like ordinary civilians, and there are banners on the tank. So what seems to be happening here is that actually this is a marketing exercise for a betting company. So that's some context which humans can understand, but again, it's quite challenging to build that kind of contextual understanding into an AI system. So, in fact, I will argue that the best forms of AI need both computational intelligence, machine learning, which I'm going to talk about in a minute, to recognize the components of that image, but at the same time, knowledge-based intelligence to give you the contextual understanding. So let's move on now to machine learning. And the key technique of machine learning, as I mentioned earlier, is neural networks. They are essentially used for pattern matching. And the main purpose of that pattern matching is classifying. So, for example, you present a neural network with images of cats, dogs, rabbits, wolves, sheep, multiple examples, and then present it with a new image and say, yes, I recognize that category. That's the category of dogs, the category of cats, the category of sheep, whatever. So recognize it or classify it. Also used for predicting, which is very similar. It's just your classes then tend to be the class that leads to the future scenario A or future scenario B or future scenario C. Clustering is slightly different, where it's actually clustering sets of inputs together, recognizing that some inputs are similar to each other and sort of grouping them together. And in general, the general purpose, you might say, is nonlinear mapping. That's mapping sets of inputs to sets of outputs. More recently, machine learning's been used for generating new artifacts. So large language models have been in the news recently, specifically ChatGPT, released last year. And I'm going to cover today three broad network types. Multi-layered perceptrons, introduced in 1986, convolutional neural networks, and then more recently, generative adversarial networks, which are starting to used to generate new artifacts. So neural networks are loosely inspired by biological neural networks, which are the basis of our own brains and spinal cord, etc. But it is just a loose inspiration. It's not an accurate model. And now the multi-layered perceptron, not the first type of neural network, but I would say it's the first practical, useful type of neural network. And it became a useful type of neural network in 1986 when Rumelhart et al. Published the backpropagation algorithm, an effective way of training such a network. The structure of these networks is that you have a set of inputs and a set of outputs. And in between, you have these simple processing nodes called neurons, and all these do is take the sum of their inputs pass it through a simple function called the transfer function, and then send it to the outputs. Each of these connections has a weighting on it, a numerical weighting. What you do to train a network is to iteratively present sets of inputs and the desired outputs and adjust the weights until the outputs match as closely as possible the desired outputs. That is the process of training. Then when you present the network with something new, something it's not seen before, it'll produce an output which is hopefully close to the appropriate output for that particular set of inputs. So that's the way the multi-layered perceptron works. Most typically used for classifying, as I mentioned earlier. And I will give an example shortly. But there are other forms of neural networks. The Cahonin self-organizing map is a form of unsupervised learning where you didn't actually tell it your desired output. You just present the network with sets of input data over and over again, and it will cluster them into sets of inputs that it recognizes as being similar to each other. Then there's things like recurrent neural networks, where there's feedback from the output to the input, and that gives you some context in the sense that you're now have some information about the sets of inputs, or the interpretation of some inputs that have gone before. So the interpretation of these inputs x1 to x5 is influenced by the previous sets of inputs, and this is relevant in anything that's has a sequential or time-dependent interpretation. And language is a classic example, because the interpretation of each spoken word is influenced by the words that have come before. It's given context by the words that have come before. And then a more modern version of these recurrent networks is long short-term memory, which is quite a popular form of providing that kind of contextual form of network. I'm going to give you a simple example now, just to make this a little bit more tangible. I'm going to consider the example of handwritten characters, which I mentioned earlier as effectively a solved form of AI. But it's a useful example for understanding how neural networks work. So here's some examples of some handwritten characters, and indeed some characters taken out of cut out of newspaper headlines. So if you were to present those characters as bitmaps to a simple neural network, it's unlikely to do well. The reason being that you just need to slightly differently orientate the character, or make it slightly bigger, slightly smaller, whatever, and that will look like a completely different bitmap to us unless you do some pre-processing. What you need to do is pick out key features known as primitives. So in the case of characters, those might be things like the number of curves, loops, and lines. So as an example, here's some handwritten digits taken from postcodes or zip codes on envelopes. And for a simple neural network like a multi-layered perceptron to effectively recognize these, you'd have to do some pre-processing. You'd have to find the primitives. And one way of finding primitives, there are other ways of doing it, but one way of finding the primitives is to scan across horizontally and vertically, counting the white to black transitions. So in this example, if you start at the top, initially the count is 0, then becomes 1 white to black transition. Then towards the middle, where you've got the sort of the loop part of the character, you count 2. So you build up these counts as you scan horizontally, and then you do the same as you scan vertically, and that gives you a vector based on these counts, and that vector is more characteristic of the handwritten character. And if you present those those sets of primitives, that form of processed character to a multi-layered perceptron, you can get a reasonable result. And indeed, I sometimes run a demonstration where I train a network on 9 examples of each character and then test it on the 10th one it's not previously seen. And you get a reasonable result just from that limited range of characters and on a very small network. Here's what it looks like in a screenshot with its 24 inputs representing those primitives that I've picked out, a layer of hidden networks, and then 10 output neurons, 1 for each digit. So in this particular example, it's been presented with a character 0, and it's produced a high output at the node that represents the 0 character. Well, this is a simple network, and it raises the question, well, if you want to tackle a more complicated problem, do you just build a bigger and bigger multi-layered perceptron? Well, the answer is no, for 2 reasons. First of all, if you build a more and more complex version of multi-layered perceptron, all you're likely to do is to achieve overtraining. So what will tend to happen is it will become more and more expert at classifying your training set, but won't generalize effectively. So when you present it with something it's not seen before, it will not be good at recognizing that. So that's kind of illustrated here, where if there's just one input, you see it's kind of drawn a line where it's become very focused on identifying those correctly, but it hasn't generalized, hasn't identified the general pattern of these inputs. Or with 2 dimensions, you can see it's become very expert at identifying these 3 classes: class 1, class 2, class 3. It's drawn a very tight boundary around class 1. So if you're then to present it with a new input somewhere between these 2 sets of boundaries, it won't recognize it because it's become too expert, too overtrained on the training set. The second issue is that by just generating a massive multi-layered perceptron with all those connections, you'd get a computational explosion. It would just take far too long to process. So that's really the driver for the next version of next key version of neural networks, convolutional neural networks. So this is the main tool that we use today for deep learning. It effectively finds the primitives automatically, so it's doing a lot of that pre-processing for you. So that's a key thing. Secondly, it overcomes the problems of computational explosion and overtraining. And it does that by a very clever design so that not all the nodes are connected to each other. There's selective connections to manage that degree of computational complexity. And it's inspired by the catch visual cortex, which indeed has this sort of limited number of connections. So this is what it looks like schematically. So typically used, convolutional neural networks are typically used for image recognition, but the same concepts apply to other networks in other domains. So in this example, I've got my rabbit picture again. And the first sets of layers are so-called convolutional layers, featuring feature maps and pooling layers. And what those layers are doing, or these convolutional layers are doing, are picking out the features in an image. So in this case, they're identifying the presence of objects, which we know, it doesn't know at this stage, but we know are the rabbits and the flowers. So it will identify those as features in the image. And then the last stage is pretty much like the multi-layered perceptron. That's the classifier. That's where it recognizes them as rabbits and flowers. So what you're doing with the convolutional layers is effectively doing all that pre-processing that I did. In other words, identifying the primitives, finding the key features in the image, and then the classifier bit at the end is doing the recognition of what they actually represent. And if we look a little bit at the structure of the network, the bottom layer is the so-called receptive fields, and if you look at how those are connected, they're not to the feature maps, which is the next layer up, it's not 100% connectivity at all. Instead, you have these clusters of nodes. In this example, 5 by 5, so 25, which are connected to a single node in the next layer above. So this idea of very selective connectivity. So it's not fully interconnected. You have this idea of layers of abstraction where you're getting more and more information about the image as you progress through the convolutional layers. And I won't go through all these points, but the key point is that you're managing the degree of complexity. And indeed, all the convolutional layers are doing are picking out the key features. They're not recognizing what they are. So it's only the final stage, the classification stage, the bit that's like a multi-layered perceptron, that is domain specific. So that's convolutional neural networks, and their variants are definitely the workhorse of deep learning. But as I mentioned earlier, we're now seeing the advance of generative AI, which is a little bit different. Rather than sort of making a decision, such as a classification or a recommendation, whatever, we're now generating something new, generating new artifacts, whether that's text, a design, programs, artwork. And we're also seeing large language models like ChatGPT. So I'll briefly talk about how these models work. So a good example is the generative adversarial network, where you have two key components: the generator, which generates prototype outputs, and the discriminator, which is kind of like a critic trying to make them better. And I think an example would be to consider it like trying to create forged paintings by Monet, the famous French artist. The generator will have a go, generate a version of a fake. The discriminator will be like the gallery curator, who's there saying, no, that's not a genuine article. So that gets fed back to the generator, who then makes a better fake. So the generator gets better and better at creating its artifacts. The discriminator gets better and better at recognizing the fakes. And so the overall effect is that it produces better and better versions of the painting. So a summary of neural networks, primarily for pattern matching. And I've talked about their uses primarily for clustering, but also primarily for classifying, but also for predicting clustering and nonlinear mapping. Pre-trained convolutional neural networks can find the generic primitives. AlexNet is an example. So only the final stage, the classification stage, is domain specific. You've got recurrent neural networks for sequential data, and deep learning has launched the second wave of enthusiasm, I would say, for neural networks, some 35 plus years after the first wave, when the practical multi-layered perceptrons were launched. If you compare the knowledge-based versus neural network approaches, knowledge-based approaches capture explicit human expertise expressed as text and symbols, whereas neural networks have rich sources of data and are the basis of deep learning. And the two, in my view, I would argue, are complementary. Practical systems actually need both. I did say that I wanted to sort of give the historical context, and I think that's really important to see how these things build upon each other. So I've already mentioned some of these landmarks from the 50s through the 70s and 80s. The backpropagation algorithm, 1986. It was 1987 that Deep Blue beat Garry Kasparov at chess. Convolutional neural networks just before the turn of the millennium. Then we've got the generative adversarial networks, 2014, and now much more recently, ChatGPT, built on GPT-4. So why the hype now with this long history? Well, I think we've got maturing ideas, we've got lots of data, we've got better deep learning algorithms, we've got internet resources, so there's data, loads of data available from the internet. We've got faster computers, so some of the concepts that have been around for a while are now practical. And then ChatGPT, I think, has opened things up again as well. And I'll give you a brief example. I just yesterday went to ChatGPT to see what it could tell me about AI literacy. So I asked it, what is AI literacy? And it gave me a definition, refers to the level of understanding and knowledge that individuals have about AI, etc. And then it went on to say why it was important. And I said, well, what are the key components of AI literacy? And it gave me an introductory couple of sentences before giving a list of 12 bullet points. And I went back to say, well, could those concepts be clustered into a few broader headings? And then it gave me these 4 broad headings around foundational knowledge, ethics and impact, technical understanding, and critical thinking and collaboration. So not the same order in which I presented them, but very similar. And I think one of the things I want to highlight with ChatGPT and similar systems is that we've now seen another shift, and I'll introduce another Venn diagram here. Until very recently, I would say all the practical AI was both specialist and discriminative. That is to say, specialist, it just worked in a narrow domain, and discriminative in the sense that it basically made a decision. It discriminated, it gave you a classification or a recommendation or carried out some control action. Whereas now we start to see, with things like ChatGPT, generalist AI, it can turn its hand to any domain. And equally, we're now seeing generative AI is creating something new. It's not just making the decision. I need to finish up now, so I'll just quickly mention ethics, a key aspect of any kind of AI literacy. Dignam divides it down into 3 categories. Ethics by design, which is AI's ethical reasoning capabilities. So classic example that's often cited is a self-driving car needing to make an ethical decision about what to do in a crisis situation. Does it crash into the bus stop in order to and risk lives there in order to avoid risk to other pedestrians' lives or whatever, that sort of thing. Those ethical dilemmas. So you've got those ethical capabilities built into an AI system, and Stahl, in fact, has proposed what he called the moral Turing test, where an AI system passes that test if you can't tell whether it's a moral being, a moral human, or the AI system that's making that judgment. Then there are what he calls ethics in design, which is the ethical implications of AI's deployment, its impacts on society, things like displacing jobs. Is that a good thing or a bad thing? You might say it's a good thing if it's saving people from drudgery or enabling specialists to concentrate on the more interesting cases. On the other hand, you might say it's a bad thing if people are dependent on these jobs for their livelihoods. You could equally argue that it's a chance to just rethink a whole model of society that's based on people working all the time. And then there's issues around the environmental impact, which I'm going to come back onto in a minute. And then finally, ethics for design, which is ensuring the integrity of those who deploy AI. So it raises questions about what it's for, warfare being a very classic controversial application, and questions about legal responsibility for AI decisions. And indeed, you might envisage so who has responsibility for AI decisions? Is it the person who's deploying it? Is it the original software developers? Is it the people who provided the data? These kind of questions. And then you might envisage a future where AI might be so advanced that you might ask whether it has the same rights and responsibilities as humans. I said I'd briefly come back on the environmental impact, and this is a key point. Some of these massive data-driven programs are heavy on their computational demands. So this is the work of Lanelong and colleagues at the University of Cambridge, where they're looking at large language models with, in this case, 176 billion parameters. And building models like this have massive environmental impact. So check the GPT-3 version, 552 tons of carbon. So, the significant impact. And they have actually published this thing called the Green algorithms calculator at green-algorithms.org. And this example is taken from a paper of theirs, where you can see a screenshot of the green algorithms calculator, where you put in your example and it will estimate for you the carbon impact of that program. So just revisiting our spectrum of intelligence, I think with these new families of AI techniques, we are now seeing the bridging of the intelligence spectrum. And by way of conclusion, I think AI literacy will become a vital life skill, like numeracy, literacy, IT competence, etc., and it applies to all disciplines, not just computer science. I think to understand AI is best understood in a historical context, as each AI development has built upon the previous ones. And I think AI techniques are complementary. Don't rely on the data alone. Knowledge-based approaches to AI provide context and understanding. And you have to be aware of the ethical, legal, societal, and environmental considerations, and they are complex. I will finish off with just a promotion for my book. It's now in its 4th edition, and I have some tools to support the book available at adrianhopgood.com/AI toolkit. And don't forget that the slides for this presentation are also available at adrianhopgood.com. Thank you very much for your attention. I'll be happy to take any questions via email. You can just Google me up. You find my name very easily, or visit my website to find my email address there. Thank you very much.